Okay, so let's talk. This is an example from Jeff Leake, who's a co-instructor in the class, and he had this nice example when he was covering um, uh, things like ANCOVA and looking at the Millennium Development Goal 1, which is a study related to a World Health Initiative, World Health Organization initiative studying malnutrition, and they very nicely put their data online. And he shows you how to get the data, but I also have it on the GitHub, the data we pulled on the GitHub repository for this slide, for these slides. So here's where you download the file, but I have it commented out because I have it in the GitHub repository. So here, instead, you can just read in this hunger.csv, this command right here just takes the gender variable and says, let's get rid of the specific cases where the gender took this particular value. And then here you can see a little bit about, you can see the data set. This head statement prevents you from having to type, for example, hunger bracket 1 to 10 comma end bracket to print out 10 rows. Head just kind of prints out a couple for you. It has some default number, and it's really a useful thing because it's faster to type out than the brackets. So you can, any rate, you can peruse the data a little bit. It has time, it has has region, country, gender. Let's see, and we're not going to use all of these variables, and there's some missing ones, some ones that didn't get grabbed correctly. Okay. So let's plot the percent of the population that's hungry versus time, starting at 1970, where the start of the data set was. So it's hunger year versus hunger star numeric, which is, I guess, percent hungry. And there's your plot. Okay. And let's see if we can fit this. This is a good example of this kind of sociological data, where it's often quite messy and doesn't have these super nice linear relationships like we've looked at in some of the examples. So we have, if we were to fit a linear model, then beta naught would be our percent hungry at year 0. Which again doesn't make any, so let's just remind us that doesn't make any sense, right? The data set goes back to 1970, so year 0 is an extrapolation, so the intercept is it hasn't been calibrated to an interpretable value. So if you want your intercept calibrated to be an interpretable value, you would need to subtract your year by some meaningful value. You could subtract the average, and then the beta naught would be interpreted as the percent hungry at the average year in the data set. Or for time, that doesn't make much sense either in this data set. You might want to subtract by the earliest year, 1970, and then beta naught will be interpreted as the expected percent hungry, the estimated expected percent hungry at year 0 for the study, being 1970. And then beta 1 is the decrease in the percent hungry per year, and the epsilon, I think you could, so one way to think about the epsilon is everything we didn't measure, which is a nice way to think about it. It's sort of like we've missed a bunch of terms in our linear model, and they all bump up and down, and then in random ways, and we've sort of we're going to treat them all as if they were Gaussian noise. There's other ways to think about this error term, and it depends on things like how you sampled the data, randomization schemes, and things like that. But for right now, let's just say we're thinking kind of mechanistically, and that and that we missed a lot of things in this model and we're dumping them all in the error term. Okay. Okay, so the LM1 is the just the standard linear regression model with hunger as the outcome, percent hungry as the outcome, which is this variable hunger numeric, $numeric, and with hunger $year here. I prefer I prefer actually to put the data frame in the data equal statement, by the way. Of course this works as well. If you don't have the data equal statement, then the variable has to be sort of explicitly stated. You have to grab the variable from the data frame hunger and from both the numeric and the year variables. You have to grab from them if you don't include the data statement, because LM otherwise wouldn't know where to look. Here's the plot, and then you can just do lines. You can, by the way, just do lines LM1, and it'll put it in there. And there's the line. Oh, there's the line. You can see it. And there's a lot of overplotting in this plot, so it's kind of hard to tell the fit. It'd be nice to so maybe when you look at this data, you could do a residual plot and some other things to actually look at the fit, jitter some points, and do some things to see the fit. What maybe we're interested, by the way, in males versus females, so we could color. We could color males and females different colors in the data set, and there's a little bit maybe of a difference between males and females there in terms of the relationship. So let's consider it, and let's think about how we can do it using some of the tools we've learned so far. So H hungry F is the percent hungry among females, and that's and I think I think this is actually a reasonable and important consideration, gender, when considering these kinds of problems, because the different gender roles played at different in different areas of the world. This would be a very reasonable thing to do. So beta, let's see, beta F0 is the intercept for this model, which is just for girls. Beta F1 is the slope model, the slope for girls. And then we're lumping everything we didn't measure into an error term there. And then we could have the same model for males. And I know it's a little bit slightly confusing notation, but HU is for the hungry, M for male. B0 is always intercept, B something 1 is always slope, and Y something is always year, and E something is always epsilon. And okay, so what we're saying now is we could try to have these two models, one line for girls and one line for boys. Okay, and you could do that, one way you could do that, right, is fit a separate line, only considering the girls and only considering the boys, and then plot them, and then you get two lines. Okay, and then you see the males in black and the females in red. Okay, and there does appear to be maybe a slightly different slope. There's a lot of points, so that might even be significant. Okay, so that's how you would do. That's looking at this with two separate lines. Fit separately. We're going to show you how to do this within a single regression model with one caveat. I'll tell you there's an important caveat as to what it's doing. This stratifying by gender, everything's different. Intercepts different, slopes different for each gender, plus the residual variance is different, right? You have a different residual variance for each gender. So not only does it have different slope and mean parameters, it also has different residual variance parameters. Okay. So here's one way to do it so that only the intercept changes. Okay, so what I've done now is I put an indicator variable for gender equals male. Okay, so what happens? You get our outcome H is equal to beta 0 plus beta 1 plus beta 2 year. Expected outcome. If the person is male, and it's equal to beta naught plus beta 1 plus not beta 1, but that guy's gone, plus beta 2 y for females, because this term, this indicator term, would be 0. Okay, so what does that look like? That's looking sort of like this, that there should be, we're saying there's two lines, right? And it's encouraging that the lines are going down. What this is saying is that there's a line for males and a line for females, and they share the same slope with respect to year. However, there's a different intercept. Males have this intercept and females have that intercept. And if you were to subtract the two, the difference in the intercepts is beta 1. So beta 1 is the change in the intercepts between the two, whereas beta 0 is the intercept for the females, and beta 1 plus beta 0 would be the intercept for the males. Okay, so that's a way you can fit two lines with the same regression model. You've included an intercept term, you've included an indicator term for gender. You could also just include gender as a factor variable, of course, given our discussion earlier, and you've included year. And the result of that is two lines, one with an intercept for males and one with an intercept for females, but sharing the same slope. There you go. Here's we do it. And we've put in sex here. It treats it as a factor variable. And there, when you look at these two lines, I know it's a little hard to see, but when you do this yourself at home, you'll see that these are exactly parallel. And of course they're parallel because our model said year has no, there's a gender variable that gives us a different intercept for the genders, but that our slope variable, year, is not interacted with gender. Okay. Aha, but let's have lines with different slopes. So now we have an indicator for gender, and we have another indicator for gender, but this time multiplied times year. Okay? And then now let's look at what happens. So here, our expected value of our outcome for males, right, it's beta naught plus beta 1 if they're male, because that guy will be 1, plus beta 2y plus beta 3, that guy will be 1, beta 3y, and then the epsilon goes away in the expectation. Okay, and then our expected value of h, this is when they're male, expected value of h when they're female, that's beta naught plus beta 1. I'm sorry, the beta 1 is not there because that would be 0 for females, so that beta 1 is there, gone. So beta 2y would be there, and then beta 3, this guy would be 0 for females, so that guy would drop out, and so he wouldn't be there either. Okay, and so what is this saying? This is saying there's a line for males, and they have an intercept that is beta naught plus beta 1. There's our intercept. It has a slope, and that slope, notice we could just pull this out, and this is beta 2 plus beta 3 times y, these two terms right here. So it's saying that the slope is beta 2 plus beta 3. I said beta 2 times 3. Beta 2 plus beta 3 is the slope. Okay, and then here it is for females, and their intercept is beta naught by itself, and their slope is beta 2 by itself. So that the interesting part about this is that beta 1 is again interpreted as the change in the intercept, which again, remember the way we've characterized it, the intercept isn't terribly meaningful because it's the percent hungry at year 0, which we don't care about. beta 1 is the change in the intercept between the two groups. Beta 3 is the change in the slope between the two groups. And notice the variable that we include, the new variable that we included, had an indicator variable times year. Okay, so that all we did was include the indicator variable times year. And so here we fit it. We have our outcome, the percent hungry, we have year, we have gender, and we have gender times year. By the way, if you include, here's a little trick, if you include the asterisks when you do an interaction, it automatically includes the main effects. You don't have to include them. If you, instead of including an asterisk between the two, if you include a colon, 2 dots, right? If you include a colon, then it only does that. So for whatever the reason, if you want something that includes the interaction term but not the associated main effects, then you put in a colon. If you want it to include the interaction term and all the lower order main effects, then put asterisks. And there you can see now we fit 2 lines. It's maybe a little hard to see, but I think I can see it. Yeah, anyone can see it, right? Look at the difference in lines there and the difference in lines there. They have both a different intercept and a different slope. One for males and one for females. Okay. And so here is our regression output. So let's see. So females are the reference category. It's clear, right? Because we are getting coefficients for male and it's omitting the coefficients for female, so it must be setting female as the regression coefficient. So this is giving us the intercept and the slope for females. This guy is the change in the intercept for males, so that the sum of these two is the 603 and 61 is the intercept for males. And then the sum of -2 and -0.03 is the change in the intercept between genders, and so the change in the slope between genders, and so our new slope for males would be the sum of those two. Okay. Notice, of course, the two terms that ascertain whether there's a different intercept or a different slope between genders are these two, and they don't appear to be very important, which of course makes sense, because if you look at these things, they don't look altogether that different, right? There's a lot of data, so you might conjecture that the intercepts might look different, but the slopes, it clearly doesn't look like much of anything. Okay. So I just want one slide on interpreting a continuous interaction, because it's kind of hard. Not hard. Hard isn't the right word. It's like hard in the sense that programming your DVD player is hard. Though I guess no one has a DVD player anymore. If you used to own a DVD player, it's sort of that kind of hard. Not hard, but you have to look at a manual. Okay, so imagine if I have an outcome y and I have 2 predictors, x1 and x2. Okay? And here's my model. I have an intercept, I have a main effect for x1, I have a main effect for x2, and I have an interaction. And I'm not going to assume that x1 and x2 are binary. Neither x1 nor x2 are binary. So I can't do the kind of separate line type interpretations that I was doing on the previous slides. You have to think about it differently. But it's not that hard, so let's just go through it. If I were to look at y and look at if my x1 was some value plus 1 holding x2 constant, minus the idea that it was just x1 not with the plus 1 holding x2 constant, I now get beta 1 plus beta 3 x2. And if I didn't have that interaction term there, it would just be beta 1 by itself. So it's no longer the case that beta 1 is interpreted as the expected change in y per unit change in x. Instead, instead beta 1 is only interpreted that when x2 is in fact 0. Okay? And instead, if you want the expected change in y per unit change in x1 holding x2 constant, you actually need to know that whole thing. Okay? And it's, of course, convenient to think about this when x2 is binary, because then you can just say it's beta 1 when x2 is 0, and it's beta 1 plus beta 3 when x2 is 1. But if it's continuous, then you need it varies. The change in the slope varies as x2 changes. Okay. So, but notice we can get an interpretation for beta 3. Okay. So we can take the change in the expected value of y given a 1 unit increase in x1, where x2 is held at x2 plus 1, right, versus the change in y, expected change in y for a 1 unit change in x1 given that x2 is held at x2. Subtract those two, right? That's, this top one is beta 1 plus beta 3 times x2 plus 1, and this bottom one is beta 1 plus beta 3 x2, and so if you subtract those two, you just get beta 3. So beta 3 then is interpreted as a change in a change. Beta 3 is the change in the expected change per unit x1 per unit change in x2. Okay? Right? It's a change in a change. That's how you wind up interpreting intercepts, right? Our intercept for the, if our slope was the expected change when we had an interaction with the slope in a binary variable, then the interpretation of that interaction was the expected change in the slope comparing the two groups. Well, if the interaction variable isn't a grouping variable like gender, it's interpreted like this here. Okay. So yeah, so this is a change and this is a change. So beta 3, the interaction term, is interpreted as a change in a change. Okay. So here is our outcome again, which is the percent hungry. Here is our intercept. Here, IN in this case is income. We're putting income in as a variable. Okay, so here we have income, year, right? Beta 1 for income, beta 2 for year, and then beta 3 for income times year. Okay, so beta 1 is the change in percent hungry for each dollar of income in year 0. Beta 2 is the change in percent hungry in 1 year for children whose parents have no income. Again, just hearkening back to my notation here, right, in that these guys are interpreted this way with respect to, only when x2 is 0 do those guys make sense. Now, by the way, no income is probably a reasonable variable value for income, or not, there's probably low incomes that relative to the larger incomes could be close enough to 0 to call it no. Time equals 0. Year 0 doesn't make any sense. So if you want to, again, it's another one of these things just like the intercept. If you want to interpret these things, you might want to subtract the income in year from a value that you actually want to interpret it relative to. Maybe the baseline year, 1970 for year, and maybe average income for income or something like that. And then that would yield a beta 1 and a beta 2 that are interpretable at the level that you want. Okay. So then beta 3, right, our interaction term is the increased change in percent hungry by year for each dollar of income. Okay. And then this just reiterates the equation we had from the previous page, but just in this context. And epsilon, in this case, is, again, we're lumping in everything we didn't measure. And Jeff had a comment here, and this is of course very well put forward, is that interactions are kind of complicated. So you need to be careful. I almost find it's almost always useful to write out the interaction. Just to be mean, I always used to, in oral exams for PhD students, I would kind of write out some complicated interactions and ask them to tell it what it means on the board. And these are people that study statistics, and they would almost always have to write it down. What I would mention is just whenever you have an interaction, an interaction, actually kind of write out the model and see what it is. We kind of give you I give you the relevant formulas on this page right here, and if you go through that exercise, you can't mess it up. But if you don't go through that exercise and you just look at the output right away, and you think and you kind of thoughtlessly interpret the coefficients, then you can screw it up pretty easily. So I think that's the general theme of this lecture. For example, with factor variables, I've seen people screw up interpretations of factor variables by forgetting which is the reference level, or forgetting whether or not they included an intercept. And those things all very dramatically change the interpretation of those coefficients. Okay, so that's the end of the lecture, and we'll look forward to seeing you at the next lecture. Not seeing you, I guess you hearing me at the next lecture.